Alright, so welcome back. So now that we've talked about the ideas of how to compute these linear quadratic approximations for a function, let's consider it on a particular example and actually see how we can use these polynomial approximations to then actually approximate our function and see how close that is to the real actual result. So in this case, we're looking at the square root of x function. We're going to center this around the point a equals 1, right? Because we're looking to approximate square root of 1.1. So I want a value that I can actually compute the square root for that's close to that. So that's why I'm using a center around a equals 1. That's kind of my target point. So a few things here. Let's notice our function, square root of x. Of course, could be written as x to the 1/2. And since we're doing up to a quadratic, we need to know our derivatives up to the second derivative. So f prime of x would be the derivative of that, which would be 1/2 x to the minus 1/2. And we need second derivative as well. F double prime would be negative 1/4 x to the negative 3/2. Okay. And then we want to evaluate each of those at x equals 1 because we're going to need to know the value. So f of 1, of course, is just 1. F prime of 1 would just be 1/2 because the square root of 1 would be 1. Put it in the bottom, it'd still be 1. And same thing, 1 to the negative 3/2 is going to be 1. So f double prime of 1 is going to be negative 1/4. Okay? So let's compute our functions here now. All right, so polynomial of degree 1, right, is f of a plus f prime of a times x minus a. So in our example, using the f of 1 is 1 and f prime of 1 is 1/2, we would get that our first degree approximation would be 1/2, f of 1, which would be 1, plus 1/2 times x minus 1. Okay? So that's our linear approximation. We can just leave it like that. We don't need to clean it up any more than that. This is perfectly fine. It's easy to evaluate. So what would our approximation be if we used the linear approximation for the square root? P1 of 1.1. Well, if you plug that in, that'll be 1 plus 1/2 times 1.1 minus 1, which would be 0.1. So we actually get 1.05, which to 2 decimal places is a pretty decent approximation for the square root of 1.1. It's not great, but it's a pretty good one. At least the 2 decimal places, we're right on. Okay. So then let's look at P2. Let's look at P2. Now P2 is going to involve the first 2 terms of P1, and then it's going to be plus the derivative, half of f double prime, right, times x minus a to the second power. So our P2 approximation is going to be our linear approximation, 1 plus 1/2 x minus 1. And then the formula again was f double prime over 2 times x minus a squared. So f double prime is negative 1/4. Multiply that times 1/2. That would make this minus 1/8 x minus 1 to the second power. X minus 1 to the second power. And that's our second degree approximation. And we can again evaluate that at 1.1 as well. And this is one where I'm just going to kind of quickly jump on to a calculator for that. 1 plus 1/2 times 1.1 minus 1 minus 1/8 times 1.1 minus 1 quantity squared. Okay, so we get 1.04875. 1.04875. And that's pretty good when you compare it to the square root of the actual square root of 1.1, or at least as good of an approximation that a calculator can give, which is 1.0488. So now 1.0488. Now if we go to 4 decimal places, we're there. Right? If we rounded this off to 4 decimal places, we would actually be in line with the actual answer. Okay, so you can see how these approximations do improve as we continue on. In fact, you can see this a little better if we go and look at this from a graphical point of view. So if we put, first of all, our square root function as our first graph. So there's our square root of x function, right? And we're approximating this at the point 1, 1, right? That's our point we're looking at. And then our 2 approximations were y equals 1 plus 1/2 times x minus 1. Right, that's my linear approximation. And then y equals 1 plus 1/2 times x minus 1 minus 1/8 times x minus 1 quantity squared. So let me just zoom in here a little bit, and we can see how these approximations improve. Right? See, of course, that the green one's okay for a while, but it quickly diverges, whereas the blue one has a little bit better staying power. Right? It maintains the shape for just a little bit longer. Now, eventually, the blue graph does lose itself as well, but it's sticking around for a little bit longer. All right, so we can see that, things get a little better with our second degree approximation. It's not perfect, but it does last and is accurate for a little bit longer. So again, we're seeing here that our P1 approximation and our P2 approximation and the actual function there. Okay, so you can see how this second degree polynomial adjusts, it compensates. First one actually became an overestimate, so the second one actually counteracts that. It's now an underestimate. It's now going to be an underestimate. And what we would hope is that our third one will correct for that guy. Our third one should correct for if we go to a third degree one, it should correct for that. And we're actually going to take a look at that in a moment, because now we want to, in the next video, we're going to say, well, what if we want to go to a higher degree? So that's what we're going to kind of turn to in the next example.